Dark matter is the missing mass in galaxies. Dark energy can explain the acceleration of the expansion of the universe. The scalar fields that we are looking for could be either dark matter or dark energy. By introducing the ultra-cold atoms and examining the effects it produces, we may be able to explain why the expansion of the universe is accelerating and whether this has any effects on Earth. The researchers based the construction of the 3D vessels on the theory that light scalar fields, with double well potentials and direct matter couplings, undergo density-driven phase transitions, leading to the formation of domain walls. The quest for dark matter detection. Dark matter is hypothesized to consist of particles that do not interact via the electromagnetic force, which is why it does not emit, absorb, or reflect light. This invisibility makes it challenging to detect. Various theoretical particles, such as weakly interacting massive particles, WIMPs, and axions, are potential candidates for dark matter. Traditional detection methods include deep underground laboratories, where sensitive detectors shielded from cosmic rays and other particles are employed to observe potential interactions with dark matter. Despite these efforts, no direct detection of dark matter has been achieved to date. This has led scientists to explore new and innovative approaches, including the use of advanced materials and novel experimental setups. Scientists are looking for ways to detect its presence through this chamber. Dark matter is invisible and can't be captured like a physical object. Hence, it is not a straightforward task. In this new study, researchers have attempted to measure it using scalar fields. This scalar field theory proposes that dark matter might be linked to hypothetical fields that exist throughout space and have very low mass particles. If this theory is true, the properties of this scalar field could explain how dark matter behaves and interacts with gravity. Therefore, the chamber itself is not intended to capture dark matter directly, but rather, dark walls, as proposed in scalar field theory. Dark walls are like fault lines in an invisible field. The 3D printed vessels we are using as the vacuum chamber have been constructed using theoretical calculations of dark walls. This has created what we believe to be the ideal shape, structure, and texture to trap the dark matter, explained Lucia Hakamila, who led the design of the laboratory experiment. To successfully demonstrate that dark walls have been trapped, we will let a cold atom cloud pass through those walls, Hakamila added. The role of 3D printing in vacuum systems. 3D printing, or additive manufacturing, has revolutionized many fields by allowing the creation of complex structures with high precision and customization. In the context of vacuum systems, 3D printing offers several advantages. Customizable designs. 3D printing enables the fabrication of intricate geometries that are difficult or impossible to produce with traditional manufacturing techniques. This customization is crucial for designing vacuum systems that meet specific experimental needs. Material flexibility. Advanced 3D printing technologies can utilize a variety of materials, including metals, ceramics, and composites, to create components that are both strong and lightweight. These materials are selected based on their vacuum compatibility and ability to maintain structural integrity under high vacuum conditions. Cost and time efficiency. Traditional vacuum system manufacturing involves complex and costly processes. 3D printing reduces both production time and costs by streamlining the creation of components and allowing rapid prototyping and testing. The experiment simulates the conditions in space by moving from a dense environment to a less dense environment. The team first removed gas particles, creating a near vacuum. The ultra-cold lithium atoms, which had been laser-cooled to near absolute zero, were then introduced. The atoms were cooled, which made their behavior more precise. The team then fired this cloud through the chamber. If dark walls exist, the cloud's trajectory will be deflected. As density is lowered, defects form. This is similar to when water freezes into ice. Water molecules are random, and when they freeze you get a crystal structure with molecules lined up at random, with some lined up one way and some another, and this creates fault lines. Something similar happens in scalar fields as the density gets lower, explained Professor Claire Burge, one of the study authors, in a press release. Burge added, "You can't see these fault lines by eye, but if particles pass across them it might change their trajectory. These defects are dark walls and can prove the theory of scalar fields, either that these fields exist or don't. The experiment is a gamble, but even if they don't find dark walls, it's a win for science." Hachimura highlights that this experiment is a great example of how lab experiments can help us understand the universe's invisible forces. As density is lower, defects form. This is similar to when water freezes into ice. Water molecules are random, and when they freeze you get a crystal structure with molecules lined up at random, with some lined up one way and some another, and this creates fault lines. Something similar happens in scalar fields as the density gets lower. You can't see these fault lines by eye, but if particles pass across them it might change their trajectory. These defects are dark walls and can prove the theory of scalar fields, either that these fields exist or don't. To detect these defects or dark walls is a specially designed vacuum that will be used in a new experiment that will mimic moving from a dense environment to less dense environment. Using the new setup, they will cool lithium atoms with laser photons to -273, which is close to absolute zero. At this temperature they take on quantum properties, which makes analysis more precise and predictable. Lucia Hachimura, associate professor in the School of Physics, has led the design of the laboratory experiment. She explains, the 3D printed vessels we are using as the vacuum chamber have been constructed using theoretical calculations of dark walls. This has created what we believe to be the ideal shape, structure, and texture to trap the dark matter. To successfully demonstrate that dark walls have been trapped, we will let a cold atom cloud pass through those walls. The cloud is then deflected. To cool those atoms we fire laser photons at the atoms, which reduces the energy in the atom. This is like slowing down an elephant using snowballs. The system took the team 3 years to build, and they expect to have results within a year. Dr. Hachimura adds, whether we prove dark walls exist or not, it will be an important step forward in our understanding of dark energy and dark matter, and an excellent example of how a well-controlled lab experiment can be designed to directly measure effects that are relevant for the universe and otherwise cannot be observed. Designing a 3D printed vacuum system for dark matter detection. The development of a 3D printed vacuum system aimed at trapping dark matter involves several critical components and considerations. Vacuum chamber. The vacuum chamber is the heart of the system, designed to create an environment with minimal interference from external particles. The 3D printed chamber must maintain a high vacuum level to reduce contamination and enhance the chances of detecting dark matter interactions. Material selection. The choice of materials for the vacuum chamber and other components is crucial. Materials must be carefully selected for their vacuum compatibility and structural properties. Advanced polymers and metal alloys are commonly used, as they offer the necessary strength and low outgassing rates. Detector integration. Inside the vacuum chamber, sophisticated detectors are employed to identify potential dark matter interactions. These detectors might include cryogenic sensors, scintillators, or other advanced technologies. The design of the vacuum system must facilitate the integration and optimal functioning of these detectors. Cooling systems. Dark matter detection often requires extremely low temperatures to minimize noise and enhance sensitivity. The vacuum system may include integrated cooling systems, such as cryostats, which must be designed to work seamlessly with the 3D printed components. Modularity and flexibility. One of the benefits of 3D printing is the ability to create modular components that can be easily modified or replaced. This flexibility allows researchers to test different designs and configurations, improving the system's overall effectiveness. Potential impact and future directions. The development of 3D printed vacuum systems represents a significant step forward in dark matter research. By leveraging the capabilities of 3D printing, researchers can create highly specialized and efficient systems that enhance their ability to detect elusive dark matter particles. This approach not only advances our understanding of dark matter but also opens the door to new experimental techniques and technologies. Looking ahead, several key areas of development and research will be critical. Enhanced materials. Ongoing advancements in 3D printing materials may lead to the development of even more suitable materials for vacuum systems, further improving their performance and durability. Collaborative research. Collaboration between material scientists, engineers, and physicists will be essential for refining the design and functionality of 3D printed vacuum systems. Expanded applications. The principles and technologies developed for dark matter detection could find applications in other areas of particle physics and beyond, contributing to a broader range of scientific discoveries. Conclusion. The integration of 3D printing technology into the design of vacuum systems for dark matter detection represents a pioneering effort at the intersection of engineering and fundamental physics. By harnessing the power of 3D printing, scientists are developing innovative tools that may ultimately unveil the mysteries of dark matter. As research continues and technology evolves, these advancements hold the promise of significant breakthroughs in our understanding of the universe and its hidden components.